but here we go. All right. So, guys, this is the big picture for the unit. This entire unit, and let me just lay this out for you in broad brushstrokes. Guys, this entire unit is about how fast reactions go. We call that reaction rate, but we talked about that last year, and we'll make those connections in a minute. But then, guys, the big picture, and we'll get to this at the end of the unit in a couple weeks. Guys, the big picture is this. You ready? Sort of watch my hands if this is helpful. Here's the way this goes. Up until now, chemistry for you has looked like this. Here's the reactants, here's the products, end of story. Right? And we have looked at balancing equations and stoichiometry and all of this other chemistry. But guys, everything that we've done has been, here's reactants, here's products. If things get really spicy, they reach equilibrium and they go back and forth. But guys, the bottom line is you got this stuff and you got that stuff. Here's why you're going to like this unit. Guys, the thing that makes this unit really interesting is now we get to ask the question, how does this stuff turn into this stuff? Because guys, the bottom line is, if you've ever thought about it, a balanced equation is sort of like a birth announcement and an obituary, right? Here's where it starts, the bouncing baby boy, and then here's the old wrinkled dead guy. It's really like that. It's beginning and end, but it doesn't tell you anything about the richness of what's going on as reactants turn into products. Guys, that's what we get to do in this unit, is talk about how do reactants turn into products. And those are called reaction mechanisms. And what you're going to be able to do in this unit is this, and this is where this gets cool. You're going to go like this. I'm going to take this reaction and I'm going to do this stuff to make it speed up and slow down. And by speeding it up and slowing down, you can figure out what's going on in the background, how reactants turn into products, and you will be able to verify reaction mechanisms saying, yes, in fact, this is how reactants turn into products. Did you pick that up when you did the reading at all? Mechanisms, chapter 15? No? Yeah? A little bit? I've got my work cut out for me, don't I? Yeah, because you've got to understand all of that stuff. That's what makes teaching an adventure. Okay, so guys, bottom line is this. Here's the way today is going to go. We are going to do some introductory stuff with reaction rates. We're going to define some terms. We're going to talk about some interesting observations. Then we're going to wrap up the day by learning to write rate expressions. You may want to, if you're titling your notes, you may want to underline or circle this or something and write a little note to yourself so when you're going back to study for the test, you may want to make note to yourself and say to yourself, don't overlook this. And guys, here's why. You guys have done enough AP type questions by now, right? What do AP free response questions look like? All the time, regardless of the topic. What do they look like? What do they all have in common? AP free response questions. Absolutely. They all build on each other, right? If you haven't picked up on that, guys, you're not tuned in. The questions on AP tests always build on each other. So answer A, then use it in B. Then answer B and use it in C, and they keep building on each other. Guys, let me tell you what's going to happen to you on the test. You are going to get to the reaction rate question on the test, and the first thing that it will say to you is this. Write the rate expression for the reaction. And here's what you guys are all going to do. Let's see if I can write on my board. Come on, baby. Here's what you guys are going to do. Instead of writing the rate expression, you are going to write the rate law. So you may want to write this by rate expression and then put an X through it. Guys, and here's why you're going to make the mistake. The last 3 days of this unit are all about rate laws. And you're going to get really good at rate laws. And you're going to be writing rate laws and doing rate laws and figuring out rate laws. And then the first question on the test is going to be write the rate expression. And you are going to blindly write the rate law because that's the last thing you did. And we've stressed it and you've become really good at it. And this becomes an afterthought. Guys, don't blow off rate expressions. You're going to see they make a lot of sense in a few minutes. But guys, as you're studying for the test, draw your attention to this so that you get those easy points early on in the test. You good to go? Okay. So guys, let's do this. Let's start by reviewing. Do you remember when we did reaction rates last year? Do you remember the lab? No? Oh, that makes me sad. I made this lab up on my own and I thought it was pretty good. So guys, let's go back and let's talk about the lab that we did last year for reaction rates. It involved Alka-Seltzer tablets. Ah, okay. So there you go. So if you remember what we did, we put the Alka-Seltzer tablet in a dilute solution of hydrochloric acid, and then when they reacted together, it generated carbon dioxide. What'd you do with the carbon dioxide? Do you remember? You bubbled it through the water that you put phenolphthalein indicator, actually you put methyl blue indicator in, and when it turned from blue to yellow, you then said that was going to be your indication of reaction rate, because the faster it went from blue to yellow, the faster that carbonic acid solution became acidic, and therefore it was a general sense of reaction rate. You remember that? So the first time you did it, you followed my directions. Then the next 3 times that you did the reaction, you got to change whatever you wanted with the outcome of making the reaction go faster. Do you remember what you did to make the reaction go faster? Crush the tablet, heated up the water. Yeah, so actually you didn't add more acid, you added less water. Do you remember? Because the first trial that you did, you diluted the acid in half. So it was 50% acid and 50% water. And then I think most of you, because you're the brighter of last year's group, figured out that what you could do is not dilute the acid, go 100% acid, 0 water. And guys, what did you find out? Did all 3 of those things make the reaction faster? They did. So guys, I would propose to you then that you can then answer the question that's coming up in a second. So what we're going to do is we're going to talk about chemical kinetics. So chemical kinetics is the study of the speed of reactions, which we call reaction rates. So if you need that as a definition, we are now going to engage in a process like we just did in that conversation, where we're going to talk about chemical kinetics, speeds of reaction or reaction rates. Now guys, without knowing it, you all just offered the answer to this question. Fundamentally, what are the factors that influence the speed of a reaction? Go ahead and write them down. Temperature and concentration and surface area, which we are actually going to call, you'll see in a minute, we are actually going to call this the state, the physical state of the reactants. And guys, again, you can feel free to write these down. We've got temperature, concentration, physical state, which includes surface area. And then guys, there was one other. Yeah, catalyst. The presence of a catalyst. And guys, let me just tell you, we are going to spend the better part of the day on catalysts. And you are going to get very frustrated with me because I am not a catalytic chemist. I think catalytic chemistry is fascinating. But guys, I know just enough to teach you what you need to know to be ready for the AP test. So what we're going to do when we go over catalytic chemistry is we're going to be fascinated together, because I'm definitely not going to be the answer guy. But I tell you what, you could make a really interesting life for yourself if you chose to become a catalytic chemist. It's really interesting stuff. Okay, so let's see if you can agree with this laundry list. So first of all, and again, you don't need to be writing this down because you already did, one of the things that determines the is concentration. We'll talk about why in a minute. The next is temperature. We'll talk about why in a minute. The third is the physical state of the reactants. Again, things like surface area and crushing. And guys, now we're ready to talk about why. Here's why I skipped the whys in all 3 cases. The answer to the why is the same for all 3. Why does increasing temperature make the reaction go faster? Why does increasing surface area make the reaction go faster? Why does increasing concentration? Why do these three things make them go faster? There's one unified answer, and what does it all have to do with? Actually, no. That's what a catalyst does. Go ahead, Vanessa. Of what? Guys, it's all about collisions. That's the big idea. If you want something to write all over this so that you don't forget, it's all about collisions. And Vanessa mentioned frequency. But guys, it's not just a question of frequency, it's also a question of magnitude. And this is where Hunter's idea comes in. Because guys, not only do these reactants have to have collisions, they have to collide hard enough. Hard enough to do what? You learned this last year. Get over the hump, which is the activation energy hump. So guys, let's do the complete review from last year. Concentration, is that a frequency or a magnitude or both issue? Does increasing the concentration increase the frequency, the magnitude, or both? Frequency. That's a frequency issue. You may want to scratch it down if you don't remember. Concentration is a frequency issue. If there's more of them, they're going to collide more often. What if there's less of them? They collide less often and it slows down. Guys, what about temperature? Is that a frequency or a collision issue? Both. Because when you heat them up, they move faster. Especially given what you now know about kinetic energies, you now know that as they're moving faster, they will of course collide more frequently, but they now have higher kinetic energies, making more of those collisions effective in getting over the activation energy hump. Now, what about the physical states of the reactants? Guys, that is a frequency issue as we think about things like surface area, because you grind them up, there are more places for contact, and therefore a higher frequency. Now guys, let's throw in the last one, catalysts. So let me give you a working definition for a catalyst, and then we'll spend, like I said, the better part of a day on it. Guys, catalysts are spectators. But don't think of spectators in the same sense that we talk about spectators when we're writing net ionic equations. A spectator in a net ionic equation does nothing. When we say spectators in this case, we simply mean substances that encourage reactions to take place, but they are not a reactant, nor are they a product. They do get involved in the reaction. Sometimes as a surface, sometimes as something that binds and then immediately lets go. But guys, they do get involved in a reaction, unlike spectators in aqueous chemistry. They do get involved, but they're not a reactant, they're not a product. They are a substance that encourages the reaction to go faster. And we'll talk more about how they do that when we spend that day-ish looking at catalysts. Are we good? Okay, so guys, what we're going to do now is this. We're going to define a term, and then we're going to start talking about reaction rates. And as we do, we're going to make an interesting point that's going to carry us throughout the remainder of this unit. And then we're going to kind of hone things down and focus our understanding a little bit, and then we're going to learn to write rate expressions. So you guys ready to go? Okay, so before we start talking about reaction rates, we need to talk about speeds of reactions. So guys, let's talk about speed. If you've taken physics, you understand that there's a difference between speed and velocity, right? One has a direction and the other doesn't. We are going to worry about direction. But we're going to talk about speed and rate as being the same thing. Understand that when we talk about direction in reaction, we understand the reactants are consumed and the products are formed. So in that case, there is a direction component. But we're not going to talk about velocity, but we are going to say speed and rate are interchangeable. So guys, bottom line is this. Speed or rate is change that occurs in a given interval of time. So guys, you tell me, what are units of speed or rate that you're familiar with? Miles per hour, right? The speed of your car. Can you come up with others? Meters per, what do we measure in meters per second? If nothing else, the speed of light, right? Because we know it's 6 times 10 to the 8th meters per second. Is that right? No, 3 times 10 to the... Yeah. It's that number. Yeah. Guys, what else? Can you come up with others? So distance over time would be speed. Let's not do distance and time. Can you give me other units of speed or rate? Say it again. Okay, so how much you grow, inches per year? Yeah. Where on earth have you ever used that in your life? It brings me back to some deep-seated issues that I have with math teachers about why they teach us radians in the first place, to be honest with you. Not in my world. I know. They tell you that because they want you to believe they're important. They're really not. Am I the only one that feels this way? Okay. So guys, what about this? What about revolutions per minute? Some of you are about to have an aha moment because in your cars there's the speedometer, right? And then there's that other dial that some of you don't know what it means. That's revolutions per minute, not your tires. It's how fast your engine is spinning, right? Okay. So what about the one that means the most to me right now, which is actually the cadence meter on my bike? Because not only do I measure how fast I'm traveling across the ground, it's also important for me to know how fast my pedals are spinning. And so I actually have a magnet that attaches to the crank arm of my bike and then a little sensor that sits on my chainstay. And it actually tells me how fast I'm pedaling, because what you want to do is stay in a sweet spot that is the most biomechanically advantageous, which is about 90 to 95 revolutions per minute. How about that? Others? How about, let me give you one other. Did you guys know I was a river guide in college? Yeah, and so every morning when we would get up, this was, my age is about to show, pre-internet. There was a time when there was no internet. We would get up every morning, and before we would float the river, we would call the flow rate hotline, and we would find the flow rates for all the rivers that we potentially could guide on so that we would know the best place to go. And so it would say the water coming out of the north gate is flowing at 1300 CFS, cubic feet per second. So guys, we've got all of these different things that give us a sense of rate or speed. Cubic feet per second, cycles per minute, miles per hour. The question is this: what do they all have in common? What do all speeds have in common? Time. And guys, that's the thing that you've got to understand. All of these things are in relationship to time. So similarly, and heaven knows you don't need to write this down, we can figure out how fast reactions are going by relating what is going on inside that reaction to time. But what are we going to track about a reaction to figure out how fast it's going? What do reactions do? Fundamentally, what do? They consume stuff and they make stuff. So if we want to know how fast a reaction is going, we can either measure how fast the reactants are going away or how fast the products are forming. Traditionally, what we'll do is measure how fast the products are forming. You'll find out in a minute the relationship between the two is what we call a rate expression. Did you catch that? What is a rate expression? It's an expression that tells us the relative rate of the consumption of reactants to the production of products. But guys, here's the trick then. We then understand that if we're going to track how fast products are being formed, what units will we use to measure the amount of product that's being formed? How do we measure amounts in chemistry? Not grams, moles. So guys, what we're going, and we'll get to molarity in a minute, but guys, what we're going to do is we are going to measure amounts in moles, but then if we want it to be a rate, what else do we need? A time, so per a time unit. And guys, obviously minutes and hours are not reasonable units. They're way too long, so we will use the units moles per second. Get the idea? Okay, so guys, with that said then, we're going to get all sorts of hypothetical here. And I love that this is actually, you'll see the picture, it's actually cast in mason jars to show you that this is really hypothetical. But for you to initially understand the idea of reaction rates, we're going to talk about a simple hypothetical reaction where red things become blue things. Okay, so this then would be our representation of this process. So this is our balanced equation. Red things A becoming blue things B. And what we have here is what is meant to represent a time-lapsed photograph, if you will, of how this process proceeds. So guys, let me zoom into this and let's talk before we get going. So the idea then is this. If you look in the left-hand portion of this, if you look over here, what do you notice about that mason jar? All red, right? It's all reactant. And doesn't that make sense that before a reaction starts, because this is at time 0, before a reaction starts, you've got all reactant and no product. It's kind of the definition of reactants and products. Now guys, and we're going to go minutes, doesn't really matter, we'll just pick a unit of time. We're then going to go 20 minutes later. And what do you notice about the amount of red? Went down. What do you notice about the amount of blue? It went up. Now guys, look, you remember this, right? A turns into B. So guys, this is a 1-to-1 ratio. So every A that is no longer there is now a B. So what do we know about the amount of A and B when we add them up overall? It's always the same because A is becoming directly B. That's not always true, but in this case it is. Now guys, notice 20 minutes later. What happened to the amount of red A? Went down more. What happened to blue B? Went up more. Okay, so guys, with that as a background, let's actually look at some data. Again, respecting the idea that this is hypothetical, but it drives home an important point. So guys, if we were able to actually count these dots and use them as a relative representation of moles, this is the data we might collect. At time 0, let's say that we've got 1 mole of A. How much B do we have? 0, right? There's no B at time 0. Now when we move on to 20 minutes later, what happened to the amount of A relative to 1 mole? It went down, right? Because that's what happens to reactants. They get consumed. So A went down to 0.54 moles. Where did the A go? Turned into B. So do the math, and how much B do we now have? 0.46 moles. You get the idea? Okay, now guys, important learning point from mason jars. Watch close. How much A did we lose in 20 minutes? How much A did we lose in 20 minutes? 0.46 moles. It turned into B. 20 minutes later, how much A will we lose? Another 0.46 moles? We will not. Guys, it actually goes down to 0.30 moles. And now how much B will we have? 0.7 moles. So guys, look at what happened. In the first 20 minutes, and this really happens in reactions and not just in mason jars. This is important. In the first time period, 20 minutes in this case, we lost 0.46 moles. And then in the next 20-minute period, we lost 0.24 moles. We lost less reactant. The question is this: why? What is fundamentally happening to this reaction? Go ahead, Keelan. Did that make sense? Go ahead. Partially, absolutely. So it's partially an interference issue. Go ahead, Eliza. Yes. Guys, do you see that? Pause there and make that make sense in your head. And Carson, you're not wrong. There is an interference issue. But it fundamentally comes down to the fact that there is a decreasing concentration of reactant. Guys, join me at the board and check this out. If you look right here, there's a bunch of A, right? you're going to have a pant load of collisions. But as these collisions happen, what happens to the amount of A? It goes down. And as the amount of A goes down, what happens to the frequency of the collisions? It goes down. So what is happening to this reaction over time? It is always slowing down. For some of you right now, you're starting to get a nervous twitch because you're starting to go, this sounds a whole lot like the first derivative of concentration. It is. But we're not going to talk about that. It's that same principle where they ask you those questions about it. You got a bucket of water and you poke a hole in the side and you're filling it from the top, and how long does it take to drink? Why do they? It's never mind. Don't go there. But guys, here's what we've got. We have got a rate that is ever decreasing because the thing that determines the rate of the reaction, concentration, is forever decreasing. It is, in fact, the first derivative, which you don't have to understand. But guys, somewhere in your notes, again in big block letters, you want to represent the idea somehow to yourself that reactions are always slowing down. And believe me, guys, we get to say always, because reactions are always slowing down. Assuming that we're not interfering and pumping in more reactant, that's kind of what chemical engineers do. But guys, reactions are always slowing down. But Eliza, remind us why they're always slowing down. Because the concentration is always going down. But guys, the concentration of what? The reactants. It's worth including that term. So guys, the important idea now that you now understand is that reactions are always slowing down because by definition they are consuming the very reactants that determine their speed. Kind of sounds like half-lives, doesn't it? It is. And we'll make those connections later. Yeah. So, yeah, I mean, I don't want to run down that path a lot, but similarly to the way we talk about the idea that when we talk about half-lives, 0 remaining nuclei is an asymptote. Technically, that's also true in chemical reactions. They get so close that we consider them to go to completion, but statistically, at any given moment, there will be some uncollided reactant. We don't worry about it, but in fact, technically, that is the case. Just a second, Eliza, go ahead. Okay, now here's where we've got to be careful because, it's interesting, what you just said is going to be our bridging concept into the next unit. Because this is why we're doing this now. We're talking about reaction rates, reactants turning into products, right? At equilibrium, we then have a competing rate where products are turning back into reactants. And what we're going to do is we are going to write the expression that compares the forward rate to the backward rate, and that opens up a whole new world of understanding in terms of what's going on at equilibrium. So we're not going to do that now, but it's the first thing we're going to do in the next unit. But your thoughts are good, yeah. Mm-hmm. Why?
Well, if the gas is like above the liquid,
Yes.
then the concentration of the reactants is
So why would the reaction not just, because it's not an equilibrium process. Again, we can't do equilibrium yet. But if you've got a reaction, like the reaction that we talked about, let's just do HCl. Oh, really? Let's just do something like this. Let me see if I can clean this up and go back here. And then let's do this. So for example, if you've got the idea, please work, of HCl plus, I'll just put sulfide here. It could be Na2S. So we end up with H2S forming, which is a gas, right? So given this, tell me what you're thinking.
So like do like mason jars, so you have all the red ones, and then
I shouldn't have tried. Keep going.
what if you, so then like halfway through
Yeah, okay.
What are those blue dots, just like for, it's how so like red dots just don't react.
Okay. Oh, so maybe the better way to talk about this would be if we really went back to this. So what you're basically saying is instead of trapping the blue goes away. So what?
So would it slow down?
No, absolutely not. Because the amount of B that's there doesn't affect the rate at which A is becoming B. Understand that completely changes when we talk about equilibrium, because then you get that feedback process. But in terms of a quantitative reaction, one that goes to completion, if B goes away, it doesn't matter. Yeah. Are you good with the fundamentals there, guys? Are we okay?
So that's because the amount of A is becoming less, so the concentration is still going down.
Correct, exactly. And maybe, Eliza, that's a good way to wrap that thought up, is the only thing that, other than temperature and surface area and things, but relative to concentration, the amount of B doesn't affect the rate at which collisions are happening in A because of concentration. Yeah, go ahead.
This idea was sort of turning around in my mind. I was assuming that maybe for some reason it wouldn't go to completion, it becomes exponentially less and less. What you're saying?
Likely to happen.
Yeah.
Yes,
So
right.
I thought it was because maybe the energy wasn't evenly distributed, but then I thought, no, that wouldn't work because you said what happened, and then I thought, would it be fair to think that at C it would take more energy in a sense to make the red particles react?
No, because the amount of energy that it takes to get the particles to react, as Hunter got us thinking earlier, is strictly dependent upon the activation energy hump, and that doesn't change relative to concentration. So that would not be true. Yeah, well, it's not pertinent to this. You guys okay with the idea? Okay, so guys, now what we're going to do is this. We're going to graph this data. Picture what that's going to look like. So the x-axis is going to be time, the y-axis is going to be amount, and we are going to graph the amount of A and the amount of B over time. So guys, fundamentally, what is that line going to look like for A, starting on the left and going to the right? Here's time 0, here's time infinity. What is that line going to look like for A? It's going to go down, right? And what will it look like for B? It's going to go up. But guys, will it be straight lines? What will those lines look like? They're going to curve. So what will the A line look like? So, and the B line, you get the idea. The idea being, guys, that these are not linear relationships. So why are these, again, what is the fact that these lines are curved bring us back to about the fundamentals of reactions? They're slowing down. And guys, now if you start to think, and please forgive me if you don't like thinking calculus, but realize that if we could take the slope of this line at any given point, which is really the first derivative, right? So guys, if you could take the slope of that line at any given point, what is happening to the slope of this line? It's decreasing, meaning that the rate of change is decreasing, the reaction is slowing down, and similarly that's true of the red line as well, although it's a negative slope because it's curving down, showing that the reactant is being consumed. Do you get the idea? Okay, so now guys, let's talk about this. We can actually then, and we don't have to do this, but we understand, I hope, well, maybe we should do this, at least this much. So would blue, let's go green. I know you hate green. Let's just do black. That'll show up okay. Okay, so guys, let's do a real quick slope thing here. So the slope of the line is rise over run, right? Yeah, okay, good. Okay, so what is our rise measured in? That is in moles. What is our run measured in? Our run is measured in time, in this case or minutes, but it doesn't matter. But guys, those are our rate units, right? Time, moles divided by time, that's a unit of rate. So the slope of these lines gives us the rate of the reaction. And again, the idea is that because these are leveling out, it shows us that the rate is decreasing, the reaction is slowing down. Now, guys, the idea then is this. What if we could do this and we could figure out the rate at that point? Right? We could do the instantaneous rate. That's really the first derivative. And then if we could similarly do that there, and if we could find the instantaneous rate of this line, the slope, how would these two slopes compare? One would be negative and one would be positive, but numerically they would be the same. So the rate at which A is getting consumed is equal to the rate at which B is getting formed. But as Spencer pointed out, this one would simply be negative because it's downward sloping because it's being consumed, and that would be positive because it's upward sloping is being produced. You get the idea? It's a significant thought though, guys. And so here's what we understand right now. Reactions are always slowing down because their concentrations are always going down because the reactants are being consumed. And then in simple processes like these, the concentration curves for the reactants have negative slopes. The concentration for the products have positive slopes because reactants are consumed and products are formed. You okay? You guys good? You good with the ideas? Okay, so guys, let me show you then what we're going to do with this data. Do you have calculators? If you do, grab them. So I'm guessing that you probably, well, let me cue you about when you want to write this down. So guys, mathematically then, we can talk about rates as being changes. Please don't write this down. So we can say that the average rate of a reaction then is the change in the number of moles, this case B, which is our product, divided by a change in time. So guys, we can simply write it like this, and this you may want to write down. It's change in moles over change in time. Now guys, let's make sure we're clear on this. How do we always measure change? It's a subtraction. What minus what? Other way around. Yeah. Times a negative, that's right. So guys, maybe it is worth writing down. Change is always final minus initial. Doesn't matter what change you're talking about. It is uniformly always final minus initial. So maybe rather than writing down those two statements, you could just write a note to yourself, final minus initial. Did you get it? Because I'm going to have you run this equation really quickly. Can I go? Okay. So guys, coming back to our data, what I want to do is I want some numbers. We need to have some numbers to compare here. So I'm going to have you guys run some calculations. So we basically have 6 groups, which works out great. So let's have Jay, let's have your group. So I'm going to assign you to oh wait, we have 8. We'll make it work. So I'm going to just go down the aisle, and if you guys then become a group, but each of you do them individually. So Jay, your posse is going to handle this interval, and then we'll have yours do this interval. Nate, yours will do this interval. Caleb, let's have all of y'all. Let's just go Caleb and then over here and then into this area. You guys all do this interval, okay? And then Eliza, you guys will catch this interval, and then you guys up front will catch this interval. And guys, what I need you to do is calculate the rate of the reaction over the interval that you were assigned. And let me make this bigger so you can see it. So guys, do it individually. By the way, which curve are you looking at, blue or red? Blue. Because it's the rate of production of product. You okay? Do you all remember which interval you're on? You guys all done? Okay, so guys, let's gather some numbers. I've got to zoom out in order to be able to write. But let's gather up some numbers. The first thing that you're going to do is you're going to forget to add units. So let's talk about units. What are the units for the denominator? You guys not done? What are the units for the denominator? Numerator. Moles. Denominator is minutes. So guys, universally, our units are moles per minute. But now guys, let's make sure we're all doing this properly. Looking at our first interval, the first 10-minute interval. Looking at our first 10-minute interval, what would the numerator look like? It would be 0.260 or 0.26 moles minus 0 moles. Final minus initial, so it would be 0.26 moles. Then our time would be 10 minutes minus 0 minutes would be 10 minutes. And so what then would our rate be? 0.026 during our first 0.026 during our first 10-minute interval, moles per minute. Now guys, let's take a look at our second interval. Now we are 0.46 minus 0.26 divided by 10. What does that work out to? Who has our second interval? What is it? 0.020. And then guys, our next interval, we're not even going to talk about the math. What's the rate? 0.014. And then what is our next interval from 30 to 40? 0.010. Oh, sorry. Got ahead of myself. 0.010. Then guys, what's our next interval? 0.008. And then our final interval? 0.006. So guys, there's all sorts of interesting things that we could learn by doing that math. Let's focus on the thing we really need to know, and then we can talk about the interesting things that aren't really necessary. So what do you notice about these rates as we go from time 0 up to time 60? They're slowing down. But we already understand they're slowing down because the reaction is slowing down. But now guys, let's talk about units. We understand that these are in moles per minute, but are our signs correct? Are they really positive? Going final minus initial and final minus initial, are these rates really positive? They are. Because the amount of product B is going up, you'll always have a big number minus a small number. That's positive. Our time will always be a longer time versus a shorter time. That's always positive. So these are always positive. Now, what if we wanted to go through and redo the math, only look at the curve for A? What would we have to do? Simply add negatives to the front of all these numbers. Get it? No, really, do you get it? Okay, because that's all you would have to do is make those numbers negative and then they apply to A. Those are the important things for you to understand about these numbers. Now here's the thing that's interesting. Did you notice the rate at which these are slowing down is also slowing down? Don't need to get into that a lot, but guys, the idea here is that because this is not a linear function, it's based upon the derivative. The rate at which it's slowing down is slowing down because there's an exponential nature to the rate at which these slow down. And we're going to talk about that later in the unit. You good on these ideas? Okay. So guys, with all of that said, we need to change the game. And here's why. What we just went over is impossible. This is where the stupid mason jar hypothetical stuff needs to go out the window. Because, guys, these concepts are solid. Obviously, if they weren't, I wouldn't have introduced them to you or stressed them the way I did. But, guys, here's the problem. This entire process that we just talked about is impossible to do in lab. Let's look at why. Where did this data come from? Well, guys, this data came from a bunch of stupid mason jars, right? And here's the problem. In order to collect data, even though we really didn't do it, but in order to collect data, what did it rely upon our ability to do? Count balls. Count moles of balls. And guys, maybe you've never thought about this, but you have never actually measured a mole. It's impossible. You can't count in moles. You can measure in grams and convert to moles. You can measure gas volumes and convert to moles. But guys, there's no such thing as a mole meter. So all of this stuff that we just talked about is impossible. You can't actually measure reaction rates in moles per second or minute or whatever. The numerator of that fraction can't be moles because we can't measure moles. So what are we going to do? What are more practical units? Here, let me just switch slides. Guys, what are more practical units for us to use to actually measure rates? If we can't do moles, what are we going to do? The problem with grams is you have to stop the reaction. You got to go stop and then weigh it. And you can't do that. So grams isn't going to work either. Guys, what is a more practical unit than moles or grams per second? You need something you can measure in lab, and you need something you can measure on the fly. What's it going to be? In what units? What are our units of concentration? Molarity. Can we measure molarity in lab? On the fly. You'd better know this if you're in second period. You'd better be nodding your head, yes, of course I can measure concentration in lab on the fly. How do you do it? Shine light through it. Remember the lab? Come on, kiddos. Remember, that's the whole idea behind Beer's law. You do it, it's funny, but guys, seriously, you should have thought of that. You do it by absorbance. So what you can physically do is you can set up, instead of blue water inside that cuvette, you can set up a reaction inside there, and by shining light through it and measuring the absorbance and the transmittance, you can actually watch the concentration change of the reactant or the product, depending on what color of light you shine through it, and you can track concentration changes over time because you can directly measure concentration over time without interfering with the reaction. Huh? But there's another way we can measure concentration other than Beer's law. Can you think of it? pH. If you're looking at acid-base reactions, guys, put a pH meter in it, because remember, pH is the negative log of hydrogen ion concentration. So we can also do this measuring pH. So guys, the long and the short of it is this, and I don't know if, well, never mind, you guys write everything down. Guys, it goes like this. Up until now, we've said that the units for rate are moles per minute, and this is actually not a useful unit. So instead, what we're going to do is we are going to measure concentration change per time, and that is going to be our unit of concentration. Typically, it will be molarity per second, or this. Okay, so now, given that we have a more practical unit for concentration, guys, what I want to do to wrap up this portion of the day is introduce you briefly to what reaction rate data actually looks like, because clearly it's not mason jars and red and blue balls. So we're going to consider a more real world, if you will, process. So guys, we're going to look at a process, we're going to study it over time, and we're going to look at reaction rate. So the process that we're going to look at is this. It's the reaction of butyl chloride with water. So guys, the balanced equation for that looks like this. You don't need to write this down. Let's just familiarize you with what data looks like. So here we obviously have water. Which one of these things is the butyl chloride? It's the thing on the left because it's the other reactant. So guys, what is this? It's butanol. How did we know that? Because we talked about the idea that an OH group makes something an alcohol, and if this is butyl chloride, by the way, but means 4 carbons, but if you didn't know that, if this is butyl chloride, then this is also but, and now it's got an OH, so it would be an alcohol. This is what is called butanol or butyl alcohol, and then there's our good friend hydrochloric acid. Now, when we look at this reaction, guys, typically what we will do is we will track the reaction of a product. In this case, they've actually given us the concentration of a reactant. So guys, if we're going to track the concentration of a reactant, what should the graph look like? Just in general, downward sloping. And so this is the data that we've got. So we've got time in, well, interesting units. It goes, and this sort of drives home the idea that this never really technically goes to 0. They say that it does, but after 10,000 seconds. In fact, it is an asymptote. But, so it goes every 50 seconds and then it expands from there. But we've got these concentrations. So they probably measured this using a light transmittance meter. And then they calculated the average rates for us, just like you did a moment ago in your little groups, where all you've got to do is take final minus initial, do the subtraction and the division. But guys, what is wrong with this data? How do you mean? Yeah, so the intervals change, but you can still do the math in between. So if you're doing an interval where it's a 50-second interval, you divide by 50. If it's a 100-second interval, you divide by 100. But guys, still fundamentally, what's wrong with this rate data? It should be negative. Right? Guys, look what's happening to your concentrations. Final minus initial. These numbers are getting smaller, which means you're taking small number minus big number, which means they're negative. Our time changes have to be positive because that's kind of the way God wired our universe. Time moves in one direction forward. So, guys, we've got negative numbers here, which means these numbers should be negative. Does that mean that they're wrong? No, it simply means that they're not respecting the fact that these things are being consumed, because the negative would simply mean consumption, but we can still talk about them empirically as being the speed of the reaction. So if we then take this data and we graph it, we end up with something that looks like this. And then, guys, we can talk about the difference between average and instantaneous rates. So, guys, when we go back to those average rates that were calculated, that would be the average for every one of these time slices. But we can also talk about instantaneous rates, which some of you probably know is the first derivative. We don't need to worry about that in this class. All we will ever calculate are average rates, average slopes, by doing final minus initial, final minus initial. When you get into college, you'll start doing first derivatives and figure out the slopes at instantaneous points, which you'll find more useful, but we don't need to worry about it in here. You guys good? Okay. So now, guys, we're going to shift gears. Now that you have a good understanding of all this stuff about rates, this is the stuff you're not going to forget about, right? Rate expressions. Here we go. You need to learn how to write rate expressions. But here's the thing, guys. You already have done rate expressions. You just didn't know it. So if we go back to this, we'll go here. So if we go back to this diagram, and remember what we did. I wonder if I can even bring it up. Let's see if I can go back there. There we go. So if we go back, guys, we have the ability to pull up the rates that we calculated between these time intervals, right? And we said these are in fact positive because we calculated them off the product B. But if we wanted to make them the reactant A, what did we have to do? Just make it negative because they're being consumed. But numerically, they were the same because every A that goes away turns into a B, right? That is actually a rate expression that says that the rate at which B is being consumed, guys, think through this with me. The rate at which B is being produced is the negative of the rate at which A is being consumed. Did that make sense? Okay. But what if it's not a 1-to-1 ratio? Well, that's what rate expressions allow you to tackle. So this is the idea. Guys, rate expressions, and again, don't confuse these with rate laws. That'll be important to you in a couple days. The bottom line is this. What these things rely upon are stoichiometric ratios. See, in the two examples we already looked at, A turning into B, and then butyl chloride reacting with water to form butanol and hydrochloric acid, these have been 1-to-1 ratios, 1 to 1 to 1 to 1. The question becomes, what if it ain't 1-to-1? And guys, this is where you need to learn how to write rate expressions. I came up with an animation. You ready? Okay, so guys, here's how you handle this. What if it's not a 1-to-1 ratio? Well, this. Let's just, and don't try to write this down, just watch. So guys, the idea is this. What if A doesn't turn directly into B? What if A turns into 2 B's? Then what's going to happen to the rate at which B is produced relative to A? Twice as fast. So how do we account for that? Well, guys, watch. Imagine that this is a molarity, not graph, but representation. So here's the way this goes. When this reaction happens, what's going to happen to the amount of A? It's going to go down. What's going to happen to B? It's going to go up twice as fast. So guys, watch. So 1A goes away, 2 B's gets formed. Another A goes away, 2 more B's gets formed. Another A goes away, 2 more B's gets formed. So as you figured out pretty quickly, the B is going to go up twice as fast as the A goes down. Now here's the trick with rate expressions. When we write rate expressions, what we're trying to do is we're trying to set these things equal. And guys, you've never maybe thought about this before. What does an equal sign mean? The same on both sides. And these are clearly not the same on both sides, and it's not just because of color. These things are not the same on both sides because that's going the wrong direction, and they're not the same height. So we've got to account for both. So guys, what can we do to this to make it point in the same direction as this? Make it negative. So if we make this negative, it then moves it up here. But now they're still not the same because this is taller than this. So how do we make them the same height? Well, we could multiply this by 2, but instead what we choose to do is divide this by 2, and now they're the same height. So guys, this is the bottom line. When you write rate expressions, what you're trying to do is get these similar rates to be equal. And the way to do that is to make the rates for the reactants negative, because that flips them over, and then divide the coefficients, and that makes them the same height. You get it? If you get it, let's then figure out what this would look like. So guys, we would write it like this. This is worth writing down. The rate expression then for this process is change in concentration of A divided by change in time. That's how we write rates, right? Is equal to the change in concentration of B divided by time. And guys, let's remind ourselves what in these expressions represents concentration. The brackets. Those are not parentheses that I happen to make with square corners. Guys, bracket means molarity. So what this is saying is the change in concentration of A divided by time, change in concentration of B divided by time. But this is not true. These are really not equal. So what do we have to do to make them equal? What do we do to the change in concentration of A? Make it negative. That flips it over. And guys, why do we make it negative? Because A is always going down because it's a reactant. So making it negative makes it positive so that it matches up with B. Now they're headed in the same direction, but they're not the same magnitude. So what are we going to do to make them the same magnitude? Divide this by 2. So we take the coefficient and put it in the denominator. So the bottom line is this. When you're writing rate expressions, make the rate expressions for the reactants negative and then divide by the coefficients. Good? Yeah.
So if that was 2A and 3B, would you put A?
That'd be the 2 in that. So let's do this. Yeah, well, I guess it's not a 3, but yes, it'd be a 2. So guys, do this. Write the rate expression for this process. The decomposition of iodic acid. But yes, what you said is true. It's always divide by the coefficients. Did you like my little animation? Not bad, huh? I should be a teacher. How are we doing? So guys, maybe then we write something like this. It always starts with rate is equal to. Then it is an expression that represents the rate, which is change in concentration divided by change in time. But notice with the HI, first of all, this is negative. Why? It's a reactant. And then it's divided by 2. Why? Because that's the coefficient. Then our next expression represents the hydrogen. Notice that we do not make it negative because it's a product, it's already going up, and the coefficient is 1, so we don't include it. And then similarly with the I2, we've got a similar expression. No, they're not added together, they're equal to, which is interesting, Nate. I'm glad you mentioned that. Because the idea is that as fast as this is falling apart, this is being created and this is being created. So they are not additive, they're equal. So what it's saying is this. This is being created as quick as this is being created. Yep, that's neat that you picked up on that. So guys, what then are you going to do with this? Well, guys, this is what this is going to look like. You ready? You're going to run into a question that might say this. What would be a good way to do this? So it might say this. I'm sort of doing this off the cuff. So say that the rate of production of hydrogen gas is 2 molarity steps. Is 2 molarity per second, okay? So that's how fast hydrogen is being produced. 2 molarity per second. How fast is HI being consumed? Let me show you how to do this. Guys, the tricky part is figuring out how do you plug data into this. Well, first of all, we can get rid of that because we're not talking about the iodine. Then, here's the way to do this. This is your variable. This is what we're given. Change in molarity divided by change in time. So this is 2 molarity per second. Now what are we solving for? Well, we want to know the rate at which HI is being consumed. So guys, this is the idea. This is your X. So what that would look like then is this. Negative X over 2. So now how do we solve this for X? Cross multiply. That gives us 4 molarity per second is equal to negative X. So if we move the negative over, that would be the rate of change for the concentration of HI. It would be negative 4 molarity per second. Again, the idea is that this is actually your rate expression, or the thing that represents rate, and then these two things are the things that actually set them equal. You got the idea? Okay. So with that said,